Hello, everyone. I'm here with Naveed Khan, and he is a machine learning engineer and also an electrical engineer, right?
Yeah.
Yeah, Pakistan. And he's actually taught me most of what I know about machine learning. And he has agreed to come on today to teach us how to make an image clustering algorithm in Python. And before we start, I just want to say he also has his own YouTube channel as well. So I'm going to post that right here called Machine Learning Insights. And yeah, already has two awesome videos on it. So anyone who it wants to learn about um, neural networks or computer vision, it's a great resource.
Yeah, thanks, James, for the introduction. Actually, you were the first student that I taught machine learning. So um, the profile that I had on Preply, you were the first one to come there, and that's when I started teaching.
Awesome. And it's
So
still
should
going
we?
well? You
Yeah,
still enjoy it?
yeah. I mean, not regularly, but
Hmm.
I do have students here and there. So
Cool.
I've been busy in some other stuff in the middle.
Yeah, you were way um, you're an awesome teacher, and also
Thanks.
underrated teacher when I found you. You know what I mean? You're amazing value.
Yeah, I don't know that, but it's good to hear.
Cool.
Okay, so should we go to the um, project? Where can I share
Yeah,
the
sure.
screen
So at
from?
the bottom there's like a present button.
Oh,
And
yeah.
you can share your whole screen, or I recommend just sharing the tab where you have the notebook in it.
Uh, Let me actually share the whole screen. Can you see the screen?
Yeah, that's good. Oh, cool. Yeah.
Yeah, so the graphic card that I'm using, the RTX 3070, I don't know what's wrong with it. There's been updates every few weeks of 700 MB, and so but every time there's a bug in the drivers. So when my charger is connected, the screen that I share, people on the other side don't see it properly. And when I unplug the charger, then the screen becomes better. So there's
Oh,
been
wow.
rapid developments on the GPU side, but because of the rapid developments, there's been lots of bugs as well.
Oh, interesting. Okay. And you bought this GPU recently, right?
Yeah, like when a year ago, I bought the laptop. And it comes with it. So the task that we're going to do here, it's quite an interesting task. Um, so the goal here is that the problem with supervised learning is that you need to have the data set needs to be labeled. So if you want to, let's say, make an image classifier to distinguish between certain categories of images, you need to have that data needs to be labeled. So you need to have a label for each of the category that you're going to start the model
Mhm.
to recognize. But like the data sets that are available online on the internet out there, not all of it is labeled.
Mhm.
Even like just quite a small percentage of it is labeled. Most of what you download is unlabeled data. Then going about doing supervised learning on it becomes difficult because it is not labeled, and labeling it is quite a cumbersome task because they are like huge amounts of it, and you need to have a human labeler in order to label it. And that's when unsupervised learning becomes handy because it doesn't require you to label the data. You can just start with unlabeled data and then you can do interesting stuff on it. So one of it is called clustering. So in the clustering, what you do is, even though you don't know what are the categories, but what you can do is recognize similar looking images together in a like separate them in a cluster. So once you do that, what it makes you able is that you can then later on take a look inside your clusters, and then you can label them by looking at some of the images in that cluster. So the data set that I'll be presenting this code on, I downloaded from Kaggle. It's of course just for demonstration purpose. Um, Anyone can then later on use it for like try the code on another data set as well. Um, but it's called animal image dataset. There are three categories inside it: cats, dogs, and pandas. So this dataset is originally like it was posted for a supervised learning task, an image classification task. Of course, we're not doing that. We are working with an unsupervised case where all the images are out there mixed, and we don't have these categories in it. Well, the goal is then to cluster similar looking images together.
Hmm.
So when I downloaded this data set, I then just mixed them all here in a single folder. So if you can see, there are images of cats and then dogs and then pandas, all of them in a single folder.
Hmm.
So by the end of running the clustering algorithm on it, what we want is that these images should be clustered or categorized into number of categories or the number of clusters that we are going to be specifying to it. How exactly how many clusters should we be, like what should be the number of clusters? That's also something which is a hyperparameter. You can like choose that yourself. But of course, when you have like lots of images, you don't know how many clusters you should be looking for. So then there are techniques to do that as well, like to figure out to at least make an educated guess on how many clusters should be should be formed out for all those images. So yeah, this is the data set, and then let's go to the coding. I've actually extensively commented this code, so you can see lots of comments here. But let's begin with the
Oh,
libraries
and is
that
this on your?
that
This
we're
is in a
doing.
GitHub. This is in a GitHub repository that you made, right? For people that are learning machine learning.
Yeah, so it's the code is there on the GitHub, on my GitHub. It's called image duplication detection. So like this is also one of the use case that you can use this algorithm for to detect duplication in the data. So suppose you have like lots of images, and the goal is to detect the duplication in it, like one image is being duplicated um, like more than once, and you need to leave the rest of the same. Okay, yeah. So basically, what I was trying to say before you lost me was that there are two basic algorithms that we are using. The first one is called VGG16,
Hmm.
which is a convolution neural network that will be useful in extracting relevant features from the images. And once we get those features, we will then feed them to a second algorithm, which is a clustering algorithm called k-means clustering, which would be basically clustering the features that the VG16 would be feeding it. The reason we are not using k-means directly on images is because images, as you're aware, are a bunch of pixel values, and distinguishing images based on just the pixel intensity values is not a good idea, because that's what um, that's what caused like that was the motivation for coming up with CNNs, uh, that the raw pixel values were not a good measure or not a good feature to be classified or to be distinguished to for the images to be distinguished from each other. So the
So
idea of CNN was that before passing the raw pixel values into the neural networks, it would be better to actually first extract some relevant features from it using the convolutional filters and then work with those extracted features.
mm,
So the idea came in around, I think, 1990s or something. And after that, its popularity actually went off the roof. So the first architecture, CNN architecture, is called Lenet. It was used for hand digits recognition, and after that, subsequent architectures came out. The second one was called AlexNet, and then after that, I think the VGG came out around
got it.
2014. So there are two versions of VGG. One is called VGG 16, another one is called VGG 19. The basic difference between the two is that VGG 16 has 16 layers, and 19 has 19 layers. So the architecture looks somewhat like this. These rectangular plates that you see here, these are the convolutional filters that are applied. And then the blue ones that you see here are called fully connected layers. Fully connected are just the simple neural networks that you see. You with me, right?
Yes, got it. So you have
Okay.
convolutional layers, and then you have the fully connected layers.
Um, Fully connected layer. So what we'll be doing is after like this last fully connected layer, you basically go with the classification. But since we are not doing the classification, we'll be removing the top from it, and we'll be just taking the output from this last layer, which is called the FC2 layer, fully connected 2. This is the fully connected first one, and then this is the fully connected second one. So we'll be taking the output from this. It would be one long vector, and each of the entries of those vectors of that vector would be basically the extracted features from the image. And then we'll take those features and feed it to the k-means clustering algorithm.
Got it.
Um, yeah, so the model is already available on the Keras applications. They contain a bunch of these popular CNN architectures like VG16, ResNet, InceptionNet, and so on. So better thing is that we can just simply import it from there and then make use of it. The rest of the packages are just simple standard packages used for plotting stuff and other things. So let me actually clear the output and then rerun this. So if you take a look at this get model method here, we're just simply calling the VG16 model. The weights that we want it to have comes from the ImageNet. So I'm not sure if I was lost when I was talking about ImageNet, but it's a gigantic image data set. People use it to test the performance of every model that they come up with. It's kind of a
Mm,
benchmark data set, contains millions of images, and every new CNN architecture is usually trained on it, and then its performance is evaluated on it. So it contains 1,000 classes, and there are millions of images in there. So the VG16 architecture that we are taking, it would be a pre-trained architecture because we are not training the VGG16 here. We are just making use of it to extract features. And that's why we wanted to have the pre-trained weights
got it.
where it was trained on the ImageNet. And then, so once we have the base model, um, the input. So here, what we are trying to do is to remove the top layer from it and only take only take the output of FC2.
Got it. So will this block take a couple of seconds or a minute to run because it has
So
to download those weights?
the model class is used. Uh, what do you mean by that?
Oh, I said, so when this block runs, it's going to actually download those weights
Hello,
from the internet, right? Oh, hello. I can still hear you.
hello.
Yeah, I can hear you. Still there?
Okay. Yep.
Cool.
Um, so the input of it is the base model dot input, and then the output. So if you see here, we are passing this FC2 string to it. So we check the base model, use the get layer method, and pass in the layer that we want to have as an output, which is the FC2. So as you can see, we are not taking the final output, we are rather taking the output of the FC2 layer.
Hmm. Hmm. Mm-hmm.
And this is going to construct the model for us, and then we just simply return that model.
Got it.
Um, this get files method is just simply going into the directory and then um, reading every single image and resizing it to the proper size. Now, this VGG16 architecture expects the input images to be of size. I think it's 224 by 224. So every image has to be resized to that shape before we can pass it to the model.
Mm-hmm.
So that's what this is doing, reading each image and then resizing it and then appending it to a Python list, and then returning that as a dictionary. So we have the file path, the file and the image being resized, and we return this as a dictionary. We're declaring these methods here, and then we'll be calling them one by one.
Got
Now,
it.
this feature vector method, we pass uh, the model and the image array as an input. So image array is just simply once you read the image, you have it as a numpy array. So we pass that to this method, and here, because the VGG16 expects each of the image to come up as a batch, to come up in batches. So that's why we expand its dimension so that the 224 by 224 by 3 is the standard image size, and then in one extra dimension converts it into a batch.
Oh.
And after that, we use the preprocess method, which we imported here. So every CNN architecture requires the images to be pre-processed in a certain way before they can perform inference on it. The good thing is that the Keras already contains that pre-processing method, so we can just simply import it and then pass the image array into it, and it will pre-process it, and then we can make use of the model.predict method and pass that pre-processed array to it and return the features. So once you call the model.predict here, if it was an image classification model, it would be giving you the probabilities of each class. But since we have removed that last classification layer from it, now it will be producing that one long vector of features, which you can then make use of to perform clustering or whatever you might want to do with the features, extracted features.
Hmm. Got it. Yeah, that's clear.
Okay, so that was for one image, and then we just simply here call this feature vector method for all the images, and the extracted features are then returned in this array here, fvect. So
How long does that take approximately for each image?
since this is like the model is already trained, the goal here is just to perform inference. So that's not going to take a lot. If you were to train this VGG16, then it would have taken a lot. But since the model is pre-trained, so it kind of takes a couple of minutes or seconds. I'm forgetting, but
Yeah.
we'll see shortly.
Cool.
So we call the get model method to produce the model, and model.summary just prints the architecture of the model. This plot model plots what the model looks like. So this is the whole architecture of the VGG16. So you have convolution layers and then max pooling layers, second set of convolution layers, max pooling, convolution, max pooling, and so on. And then we have the FC1 layer, which is the first fully connected layer, and then the FC2 layer. And as you can see, we don't have anything after that. So this is where the model would be producing its output. So the output shape that you see here, 4096, is the number of features that it would extract from each image.
Mm.
So for every image that you feed to the model, the output is 4096 features. So we just simply provide the path of the data, get files, extracts the file, the path to each to every image, and then the feature vectors method takes those image paths and the model and return the image feature vector, which are the features extracted from every image stored in this vector. The size, as you can see here, is 224 by 224. So let's see how much time it takes.
Cool. So does it also have to download the weights when you first run this?
Yeah. So because I already ran this code,
Hmm.
it didn't download it.
Hmm.
It was already cached, I guess.
Hmm.
But for the first time when you run it, it has to download it. Let's check the GPU usage. $41. Yeah, so since it's inference, it's not making use of GPU that much, but during the training, the usage is more.
Hmm. Yeah. And is this a lot faster compared to if you had run it on Collab?
So the GPU that Colab provides, if it's the free version,
Hmm.
I compared the output of like the time it takes on Colab with the GPU card that I have. It was on almost on similar scale, so it didn't like Colab wasn't able to. Both the GPUs are performing similar. Now the code has executed, so we didn't record the time, but that's how much it takes.
Yeah.
Yeah, so once we have the features extracted from every image, the next thing is now to run the clustering algorithm on it. Uh, but just like I told you, we don't know how many clusters we should be looking for. If you
Right.
have a huge amount of, if you have lots of images, you don't know that in advance how many clusters are there. So the method that is used to figure out the number of clusters is called the elbow method.
Mm-hmm.
So the elbow method already makes use of the k-means algorithm to determine the number of clusters. So we basically take a number of clusters, starting, like in this case, I started from 1 to 30 clusters, and each of the time I'm running the clustering algorithm on it with a particular number of clusters. So first we run it with one cluster, then with two, three, four, five, six, and so on. And every time we run the clustering algorithm on it, we compute a parameter called the inertia of the clustering. So the idea of the inertia is that once you figure out the number of clusters, you basically calculate the distance of every image in a cluster from the centroid of the cluster. So you have a central point, and you compute how much each image is far away from that centroid. So the goal is that the inertia that you calculate in a single cluster should be as minimum as possible. So suppose you have three clusters, you calculate the inertia in one cluster, and the second cluster, and the third cluster, and then you add all of them. And the goal is that this measure that you get, that value should be as small as possible. Now, if you increase the number of clusters, the inertia goes down, because suppose first you had, suppose there are 10 images and the number of clusters that you're looking for is 3. So if you have three different centroids and you calculate the distance from the centroid to every image in a particular cluster, let's say in the first cluster there were 3 images, you calculate the distance. In the second cluster, you calculate the distance in the third one, and then you add all of them. You get one measure. Now, if you increase the number of clusters, you have one extra centroid, which would make it even more, like the distance would even more be reduced. Um, so if you make the number of clusters equal to the number of images, in that case, the inertia is 0, because for every image, you have one cluster, one centroid sitting on top of it. But that defeats the purpose of clustering, because now you have as many clusters as you have images, which is something that we don't want. We want to cluster images together. So there should be, what you should be looking for is a sweet spot where the number of clusters are such that the inertia is reduced, but the number of clusters should not be like as much as there are images in it. So this plot that you see here, on the x-axis you have the number of clusters, on the y-axis you have the inertia. And the elbow method basically says that initially the inertia drops quickly if you increase the number of clusters. And after a certain amount, if you increase the number of clusters further, although there's a reduction in the inertia, but it's not that much. So this elbow point is what is the sweet spot where you have significantly reduced the inertia and you don't have lots of clusters. So you should be picking a point which is right at the elbow, here at the knee point. And if you see here, it's somewhere between 3 and 4. Now, because we already know that we have three different categories, I picked that to be three. But of course, I knew that already.
Right.
But if you don't know that, you would be either picking 3 or 4 and then running this algorithm one. So elbow method, although it's not a perfect, like it wouldn't come up with a perfect number of clusters, but it would be something that would be reasonably good um, to work with.
That's a very helpful visual description of how the inertia method works. It's easy to visualize in 2D. I guess I just have to, I always have to remember when you're describing it that the space of the distances are being calculated in is actually the number of dimensions in the vector, right?
Exactly. Yeah, that's a really good point that you come up with. If you see here, the number of features that it is extracting from every image is 4096. Of course, you cannot visualize that many dimensions. So what we basically do is, for the explanation purpose, we work with 2D, and then we say that the similar idea can be applied across more than three dimensions. So I didn't talk about the k-means clustering. We jumped directly to the elbow method, but the idea of k-means clustering is super easy, yet it is super powerful. So how does k-means cluster stuff together? The idea is that suppose we are working in a 2D space. So if you have a bunch of points um, dispersed across 2D space, maybe if we show it on if we ask Google, it would come up with a very nice looking image where we can explain. So suppose um,
Hmm.
we have this image here, and it's a 2D space, and there are a bunch of points dispersed across the space, and our goal is to cluster similar points together. Now, suppose the number of clusters, the k value that I came up with is 3. So what the k-means clustering does is that it randomly um, plots those
Hmm.
three dots on the space. Each of the dots is called the centroid, and then it calculates. Suppose we start with this centroid here. It calculates the distance of every point, um, every data point here with that centroid. So suppose it starts with this data point, it calculates the distance with this centroid, and then the distance calculated with that centroid and with that centroid. Whatever is closer, it just simply assigns it to that cluster. And the same operation is applied for all of the data points in the space. And that's how each of the data point gets assigned to a particular centroid.
Hmm.
Now, once you do that operation, you update the position of the centroid. And the way that you update it is that you just simply take all the data points that are assigned to that particular centroid, you take the average of the dimension, and then you replace the position.
Hmm.
The newer position is then the average of it. So initially, the centroid starts somewhere, and then after iteration by iteration, it gradually refines its position, and after a certain amount of iterations, you then notice that the positions of every point is no longer updated. So like every point that is assigned to the centroid, if you repeat the operation once more, its position is not changing. So once the positions of the points are not changing anymore, you then say that the clustering has converged, hopefully converged to something that would be fruitful enough. So that's the idea. It's really I mean simple, but yet it works wonders, and that's why even still the k-means clustering is the go-to algorithm whenever someone is doing clustering.
Interesting. So then that also means that it's not deterministic, right? You might get different results if you would run it multiple times.
Exactly. So every time you run the algorithm, the initial centroids that it is picking, it's at random. So sometimes it picks the points in one particular location, and then the second time you run it, the location of the centroids is changed. So the points might, like, every time you might get a different result, but it's not drastically different.
Hmm.
Now there's a problem that is involved with the randomly initialization of these centroids as well, and that problem was then later on resolved by what is called k-means plus algorithm. So in the original k-means, the centroids were picked all of them were picked at random at once. Uh, but there was a problem with it because sometimes you can get two centroids very close to each other, and in that case, maybe this cluster that you see here, the blue one, would get split in half uh, because of the initial positions of those centroid, because they were so close to each other. Half
Hmm.
of the points goes to one, and half of them goes to second one, and all of these points, the yellow ones and the green ones, then gets clustered to the second cluster,
Mhm.
which of course is not a good clustering, but that can happen because the points that you're picking, the centroids, is at random. So in order to mitigate that issue, the idea with the k-means plus is that you first come up with one position for the centroid, and then the second centroid that you are picking, you pick that in relation to the first one, so that it not comes very closer to the first one. So you pick the one, and then you try to pick the second one as far as possible from the
Got
first one, and
got
then the third one you pick in relation to those two. So that way you can avoid the problem with which came up with the original k-means. And that's why, as you can see here, the init method that we're using it here is called k-means plus plus, which is the improved version of the k-means algorithm.
cool.
Now, the k-means is like it comes in the scikit-learn library, so it's super easy. Its implementation, you just simply call it, provide in the number of clusters. The init method is k-means plus plus. You have the k-means object here, and then you can just simply call its dot fit method with the images. And remember, the images here are the feature vectors that we extracted from the original images. So once you fit it to the images, you can just simply call the dot predict method, provide the same images, and the output, which is the yk means, is the. Are you with me?
Yeah, I hear you. Yeah, keep
Okay.
going.
So the yk means here, yeah, I thought I lost you, but I can hear you now.
Yeah, we're good.
Okay. So the yk means here, then it comes up with the clustering number for each and every image that you have. So if we take a look inside this yk means here,
Hmm.
you just simply see 0, 1, and 2. These are like for every image, it has now a clustering number. So it's saying that these images belong to cluster 0, and then these belongs to cluster 2, and these belongs to cluster 1.
Hey, could you try actually sharing your screen again?
Okay.
Um, it looks like it just froze, but just the screen.
Okay.
Yeah. Let's see. Yeah, we're back. Perfect.
Okay. So I was talking about this yk means after you perform the dot predict method on it. So now you have a number for every single image that you had in the images vector. So these images are getting clustered to the cluster 0. These are going to cluster 2, and these are going to cluster 1. So
Hmm.
now we can make use of these labels to basically cluster our images or pick similar images into a particular cluster, copy them to a particular folder, which is what we would be doing. So here, that's what we are doing. We are creating a new directory for each of the cluster, and then taking those images which belong to that cluster, pasting it in that particular folder.
Cool.
Yeah. Now, since it is unsupervised learning, so you don't have a ground truth to actually compare uh, how the clustering is performing. Like, you don't know how to what to compare it with, so that we can have an idea of how good the clustering algorithm is. And that's why we have another way of evaluating the performance of the clustering. It's called the silhouette analysis. The idea with silhouette analysis is that since the goal of the clustering algorithm is that in a single cluster, points should be as similar to each other as possible, and all those points in the similar cluster should be as different as possible from the second cluster.
Hmm.
So um, the silhouette analysis basically calculates it takes a particular point inside a cluster, and then it calculates the average distance of that point with all the neighboring uh, points in that particular cluster. It gives it, it stores it in one variable, and then it calculates the distance of the same point, but with the points of the neighboring cluster, with all of the points in the neighboring cluster, and it takes the average of it, and then to come up with a quantity called Silhouette coefficient, it basically takes the difference of those averages, and then it divides by the maximum of the two averages. So I mean, the details are like mathematical, but the basic idea is if you get a Silhouette score of 1, it's perfect, like the clustering is performing ideally, and if you get a score of -1, it means it's performing poorly. So those are the two extremes. Um, of course, you are not going to have 1 or -1 for real world examples. It will always be in the between, and 0 is kind of the boundary. So from the 0, if you shift to the negative side, your algorithm is actually performing poorly, and if it is on the positive side, it is performing good enough. So we calculate this Silhouette coefficient for every single image or every single point in a cluster, and then we plot it to see how it performs. And that's what this code is doing here. So if we see the the three bars that you see here
Hmm.
are for the three clusters. So for the cluster 0, as you can see, it kind of looks a continuous bar here, but actually it is consisting of like every single image in the 0 cluster, the Silhouette coefficient is calculated for it, and then it is plotted as a single bar. And then the the continuum that you see here is because you have so many images in that particular cluster. So for the first image, the Silhouette value that you get is somewhere around zero point 0.3, and then for the second one, it's slightly lower than that, and for the third one, and so on. By the time you get here, it's around zero point 0.1. So for majority of the images that you see here, the Silhouette coefficient is on the positive side, so it means it's performing good enough. But of course, there are images which it is clustering not so good, and that's why the Silhouette coefficient that you get for it is on the negative side of it. And this dotted dashed um, red line that you see here is the average Silhouette coefficient for all the images. So if this line comes on the positive side, you can assume that your clustering is performing better. The more it is on the right side, the more good it is, but somewhere between zero point 0.1 and zero point 0.2 would be good enough.
Hmm.
So let's actually see how it clustered the images. So here the image that I'm plotting here are for the cluster 0. So it looks like the cats got the cluster 0, and that's why the images that you see here are all cats. And if
Yeah,
we
that
plot
makes
it,
sense.
and if we plot it for the cluster 1, pandas got cluster 1,
Looks right.
and cluster 2 were dogs. And if you see here, some of the like majority of the misclustered images were in the dogs category. So let's see.
Mhm.
You see cats here as well. So that kind of makes sense. But these are not all the images. So let's actually see inside the folder that it would have created. Yeah, cluster two. So even though this is the dogs cluster, but still you see cats here, and these are the ones that it misclassified. Majority of it are dogs.
Interesting.
So we initially started with this mixed data, and by the end of it, we now have three folders, and it has kind of picked similar images together and clustered them together.
Interesting. So, can we kind of assume from this that the dogs and if we visualize the whole vector space, that the dogs and the cats are sort of closer together, more mixed together than the pandas?
Exactly. And that makes sense because if you look at the pandas, they are visually very different
Yeah.
from how cats look like and how dogs looks like. And that is why the misclassification happened in the cluster two, where it confused some of the cats for dogs. So yeah. Now, of course, the model that we used is VGG16, but if you go towards some of the more powerful architectures like the VGG19 or maybe the Inception net, which came after it, or even more powerful is the ResNet architecture, which performed on top, like it was the best one amongst all the CNN architectures. So if you make use of a ResNet architecture to extract the features, maybe in that case, it would perform even more better to cluster images together.
Got it.
So yeah, that's all that we had here. The rest of the code here just simply plots or um, comes up with the like how many images it clustered together, and based on that, it calculates the duplication, like how many similar images
Hmm.
were there in cluster zero and cluster one and cluster two, and just plotting those things. Cluster one, two, and three, zero, one, and two.
So, what does the duplication mean?
Yeah, actually, this was kind of a use case of it. So it's not kind of the part of the clustering,
Yeah.
but so if you have like 1,000 images
Yeah.
and 270 of it went to cluster zero, you just simply take that and divide it by the total and come up with a percentage value of how many similar things were in the cluster zero. So
Got it.
um, the percent the percentage of duplication, you just simply calculate it and then plot it. But as I said, it was just a use case of it. So the original task was to somehow cluster similar things together. We did it for images, but of course, if you want to cluster, let's say, some uh, writing stuff, so maybe some blog articles, you have lots of them and you want to cluster similar ones together, the feature extractor that we'll be using, it would be instead of a CNN architecture, it would be some transform architecture. So say a GPT or something, GPT-1 I'm talking about. So you use the GPT to extract features from the blogs, and then subsequently make use of k-means to cluster the features together, and then that way you can kind of cluster similar writing articles together. And you can do the same for any tabular data set. And then the tabular one, you wouldn't require any feature extractor because k-means alone would be sufficient enough to cluster stuff together.
Hmm. Cool. That's really awesome. Um, yeah. I found this to be super super informative and right on time as well. Have you timed this before?
Yeah. So um, w- I didn't know it would. finish in 1 hour, but surprisingly, it did.
That's some time.
Yeah,
Really cool, man. Thank you so much for explaining all of that. And I've also put the link to the GitHub repository in the comments. So like anyone who's watching this, they can go onto your GitHub, Naveed 88375, and they can like download it and try it for themselves.
yeah. So thank you so much, James, for having me. Um,
Yeah.
I look
Yeah.
forward to similar discussions in the
So guys,
future.
this is Naveed again, and this is his YouTube channel, and he's just starting out on YouTube, but his videos are super high quality. So yeah, I recommend anyone who wants to learn more about machine learning should go to youtube.com/at machine learning insights. Sweet. Yeah, thanks, Naveed.
Thank you so much.
Okay.